Welcome to section 3.2, radians and degrees. In this section, we introduce the radian measure of an angle, a fundamental way to express angles beyond the traditional degree system. Unlike degrees, which divide a circle into 360 parts, radians provide a direct connection between an angle and the arc length it subtends on a circle. By using radian measure, we can associate angles with real numbers, making trigonometric calculations more natural and applicable in higher level mathematics and science. We have 4 objectives in this section. The first objective we're going to look at is measure a given angle in radians. To define radian measure, we first recall that a central angle is an angle whose vertex is at the center of a circle. A central angle measuring 1 radian is the angle that cuts off an arc equal in length to the radius of the circle. In other words, in a circle of radius r, if the arc length it intercepts is also r, then the angle measures 1 radian. So here we have a visual with a center O. We have 2 radii that make an angle theta, and the angle theta has a measure of 1 radian. The vertex of theta is at the center of the circle. The arc cut off by theta is equal in length to the radius. Omitting the unit radians, when an angle is measured in radians, we typically do not write radian explicitly. If no unit is shown, the angle is assumed to be in radians. However, if the angle is in degrees, the degree symbol must be written. For example, if theta equals 2, that means theta equals 2 radians. However, if theta equals 2 with this degree symbol, that would mean theta measures 2 degrees. To determine the radian measure of any central angle, we calculate how many times the radius fits into the arc it cuts off. This is done using the formula theta equals s divided by r, where theta is the radian measure of the central angle, s is the arc length, and r is the radius of the circle. And your image here to the bottom right kind of shows exactly where that representation of each variable would be on our circle. So in our first example, we have a central angle theta in a circle of radius r, 5 centimeters, cuts off an arc of length 15 centimeters. What is the radian measure of theta? So let's draw our circle. Okay, ooh, that was almost nice. All right, and we have our center. We have a radius r, which our problem tells us is 5 centimeters. We then have an arc of length 15. So let's just, we don't know how big theta is, so we'll just make this theta. This is theta. Let's rewrite theta. There we go. This is theta. And we have an arc length of 15 degrees. So this is our arc. And this is 15, not degrees, 15 centimeters. And we're trying to find theta. So we know r equals 5 centimeters. We know s equals 15 centimeters. And we know theta equals s divided by r. So if we substitute in s, substitute in r, we will get 3. So theta equals 3 radians. Awesome. So now let's go into our second objective. Compare angles in radians and degrees. So to understand how degrees and radians relate to each other, we can compare the number of degrees and the number of radians in one full rotation of a circle. So a full rotation around a circle center creates an angle that cuts off an arc equal to the circle's circumference. Since the circle's circumference with radius r is 2 pi r, and the radian measure of an angle is given by the arc length divided by the radius, we can calculate theta. So theta would be our arc length, which is our circumference 2 pi r, and then r is our radius, which is r. When we simplify by canceling out the r's in the numerator and denominator, we'll get 2 pi. So theta will equal 2 pi radians. So one full rotation is equal to 2 pi radians. So we know that one full rotation in degrees is 360 degrees. So we establish the fundamental conversion. 360 degrees equals 2 pi radians. And if we were to divide both by 2, we would then be able to state that 180 degrees equals pi radians. So this equation then allows us to convert between degrees and radians. So to switch between degrees and radians, we'll use the following conversion factors. 1 radian equals 180 degrees divided by pi, and 1 degree will equal pi divided by 180 degrees. So objective 3 states convert from degrees to radians. So we're now going to look at some problems where we'll be given the degree and we now need to state it in radians. So first, we're asked to convert 50 degrees to radians, write our answer in both exact form and rounded to the nearest hundredth. So 50 degrees, we know, is in quadrant 1. Okay. We know 1 degree is equal to pi over 180 degrees. So if I want 50 1 degree, I'm going to take 50 times pi over 180 degrees. It's like multiplying both sides by 50. When I simplify, I'll get 5 pi over 18. When I enter that into my calculator, I roughly get 0.87 rounded to the nearest hundredth. So these would be my two answers. The first one would be the exact form. And the second one would be the rounded or estimation or decimal form. All right, let's do another one. Convert 430 degrees to radians. Write answer in both exact form and rounded to the nearest hundredth. So 430 degrees is more than 360. All right. It lands in the first quadrant, almost hitting the 90-degree bar. So it's 430 degrees. So we know 1 degree is equal to pi over 180. And if I want 430 of them, I'm going to take 430 times pi over 180. I will simplify this and I will get 43 pi over 18. Getting the decimal, I'll get an estimate rounded to the nearest hundredth, 7.50. Okay. Both of these you can enter into your calculator. So this is the rounded form. And this is the exact form. Awesome. Okay. So now we're going to go into our last objective here, where we are going to convert from radians to degrees. So we initially went from degrees to radians. Now we're going to go in the reverse. So in our first exercise here, we're asked to convert 5 pi divided by 6 to degrees. Well, we know 1 radian is equal to 180 over pi. So 5 pi over 6 radians is going to be equal to 5 pi over 6 times 180 over pi. I can simplify this by canceling out the pi, and I can then divide both of these by 6, and this would get me 30. So then 5 pi over 6 is equivalent to 150 degrees. Okay. Next, we're asked to convert 7 pi over 3 to degrees. Well, 1 radian equals 180 over pi. I have 7 pi over 3 radians. So I'll take 7 pi over 3 times 180 over pi. I can simplify this, cancel out the pi's, divide both of these values by 3, and then simplify. So 7 times 60 is 420 degrees. So 7 pi over 3 in radians is equivalent to 420 degrees. So, as is apparent from the preceding examples, changing from degrees to radians and from radians to degrees is simply a matter of multiplying by the appropriate conversion factors. So if I want to go from degrees to radians, I'll multiply my given value by pi over 180. And if I want to go from radians to degrees, I'll multiply my given value by 180 over pi. So the following figures show the most common angles written in both degrees and radians. The table gives approximations to some of the exact radian measures, accurate to the nearest hundredth of a radian. Okay, so 0 degree is equivalent to 0 radians, which is approximately 0. 30 degrees is equivalent to pi over 6 radians, which is approximately 0.52. 45 degrees is equivalent to pi over 4 radians, which is approximately 0.79 degrees, and so on and so forth. Our unit circle here to the right showcases all of the angles and its reference angles, and they are written in degrees and in radians. Okay. All right, our next example, find the sine of 2 pi over 3. So the sine of 2 pi over 3, if we look at our unit circle here, 2 pi over 3 will be equivalent to 120 degrees. 120 degrees is going to be our angle, theta. The reference angle for that is going to be 60. So we want the sine of 60 degrees. The sine of 60 degrees is the square root of 3 over 2. Okay? So its reference angle is 60 degrees. And so if we took the sine of 60 degrees, we will get square root 3 over 2. Okay. All right, next we have 5 times the cosine of pi over 4. Okay, pi over 4 is equivalent to 45 degrees. So we want 5 times the cosine of 45 degrees. 45 is within itself a reference angle. So the cosine of 45 degrees is the square root 2 over 2. So simplifying this, we would get 5 square root 2 over 2. Let's do one more. All right, our last one. We are asked to evaluate 3 cosine 2x plus pi when x equals pi over 6. So 3 cosine 2x plus pi. And so x equals pi over 6. So let's substitute that in. So I'm going to rewrite x as pi over 6 plus pi. Oops, need another parentheses in there. I can then combine the 2 and pi over 6 to pi over 3 when I simplify it. Then I have like terms, so pi over 3 plus pi would be 4 pi over 3. 4 pi over 3 is the same as 240 degrees. Okay. All right, so the reference angle of 240 is 60 degrees. So I want the cosine of 60 degrees, which would be, so it would be 1/2. But since I'm in the third quadrant, all students take calculus, cosine is negative. So the cosine of 240 degrees would be negative 1/2. Okay? So when I combine these, I will get negative 3 over 2 as the value of 3 cosine 2x plus pi, where x is pi over 6. Okay? Awesome, that was fun.